All right, welcome to the second of two lectures in Unit 4, Deciphering the Earth's History. This lecture will cover subject matter related to the Earth's geologic evolution through time. Now, the last lecture in Chapter 11 went a little bit longer than I was hoping. I know many of you probably were dismayed to see the clock ticking past 1 hour, so I'll try my best to keep this one shorter. The geologic timescale was introduced in the last lecture as a system of compartmentalizing and dividing Earth history or Earth time into units that are related, and the boundaries that form the divisions between the time periods are usually indicate significant geologic events. Going further back in time to the Precambrian or before, to the Precambrian, which includes the Proterozoic, Archean, and Hadean eons, there's very, very little material left on the Earth's surface that was formed during that time. And if you do find, or if material is found from those eons, from 540 million years ago or before, oftentimes it's been significantly altered, eroded, and modified. Basically metamorphosed. And the further closer to the present day you get, moving up through the Paleozoic into the Mesozoic and the Cenozoic, the more material remains on the Earth's surface, or at least observable by Earth scientists, and the more information we know. We're going to start back in the Hadean, Archean, and Proterozoic in this lecture, and we'll move through time from oldest to youngest. So basically we'll be going from the period of before life. The Cambrian boundary at 542 is considered in the geologic record to represent the beginning of life on Earth. We'll move through the age of invertebrates, fishes and amphibians, which is the Paleozoic. Moving up into the age of reptiles, the Mesozoic, the kind of the middle period, and then we'll get into the most recent era, the Cenozoic. But we do have to start at the very beginning, or at least the last point at which scientists are in generally good agreement about the origins of the planetary system and the universe. And that is the Big Bang, which roughly a little bit under 14 billion years ago. The elements which were generated, fundamental elements of hydrogen and helium, and then due to cascading elemental interactions were coalescing into larger elements and molecules and compounds, occurred. Those materials or those elements, those compounds, began to coalesce and accrete due to gravitational forces. These are kind of molecular scale gravitational forces would bring them in closer proximity, and matter started to be more defined. By about 10 billion years ago, our galaxy, the current galaxy we're in, formed, and additional gravitational friction, gravitational heating, and gravitational accretion caused the solar nebula to eventually develop roughly 5 billion years ago. As that solar nebula starts to coalesce and then flatten out and rotate in a discoid. Remember, we saw this material in I believe, Chapter 1 as well. It starts to form this discoid shape. Planetary accretion starts to take place. And planetary accretion is a process by which small bits of matter, collect and collide and accrete and join together to form progressively larger masses. Planetesimals, which are small planet-forming units of mass or units of matter, coalesce and begin to form the planets. We discussed in Chapter 1 how density and material differentiation occurred in that proto solar system, where the rocky material, the less or medium density material, coalesced closer to the sun, and the gaseous elements, the lighter stuff, will coalesce further afield. The gassy planets are further out in the solar system. Now, the Earth, we can focus in on the Earth at this point. After the initial formation of the Earth, that is the rocky elements, iron, nickel, silica, aluminum, sodium, potassium, calcium, oxygen, and silica. I hope I didn't forget silicon. Coalesced; those made the primary materials of Earth. They coalesced, and you had lots of gravitational friction caused heating. You had radioactive decay heating from the interior, but you also had bombardment from lots and lots of different astronomical objects, meteors, asteroids, etc., that were continuously bombarding the surface of the Earth. This is a very violent period in Earth's history, in that 4 to 5 billion years age range. In fact, the primary theory of the formation of the Moon is that an actual Mars-sized body impacted the surface of the Earth, which caused a lot of material from the crust and maybe the upper mantle to be projected or ejected out into space. It was not ejected far enough or with sufficient force to escape the gravitational pull of the Earth. And that material eventually, just like the planetary accretion that occurred around the solar nebula, this material ejected from the Earth's crust was trapped in gravitational orbit around the Earth, eventually coalesced, forming enough of its own gravity to really coalesce into a solid planet, and actually became the Moon. The progression of the Earth-Moon system occurred or was finalized about 4.5 billion years ago. And then as the Earth starts to cool down, the magma ocean is no longer roiling on the surface. Continents start to form, outgassing from the mantle of carbon dioxide, which is emitted from volcanoes, and water is also emitted from volcanoes, starts to collect on the surface. Atmospheric carbon dioxide creates a very, very hot environment. So carbon dioxide is a greenhouse gas. It tends to trap thermal radiation that would otherwise emanate back out into space. Water, on the other hand, is also held on the surface by gravity as it evolves out of the central or the inner Earth. It migrates outward due to volcanic tectonic processes and gravitational diffusion. Is also held on the surface by gravity, and the water cycle begins and can collect in ocean basins. Now, oxygen was not present in the atmosphere early on. However, it did slowly increase in the atmosphere and in the oceans. Eventually, it was sufficient enough to develop ozone, which is an O3 molecule in the outer atmosphere that will come into play later on. It's incredibly important for respiration or respiring organisms, in that it blocks UV radiation that naturally comes from the sun. UV radiation is quite damaging to cellular structures, and so the incorporation of oxygen into the atmosphere not only made respiration possible at 500 so million years ago, but it fundamentally protects the cellular structure of animals. Outgassing of carbon dioxide from volcanoes and tectonic processes produces acidic conditions that accelerate the rate of weathering on the Earth's rocky surface. So by this point, we've got continents forming, and we'll look at exactly how continents were forming in the early stages of Earth's history. But CO2 in the atmosphere increases chemical weathering, which we learned earlier in this course. Those weathering products are actually transported to ocean basins. So downslope, as we've learned about stream flow, how streams transport material down to base level. Base level in this case would be sea level. Those materials or those elements that are weathered out, those compounds and molecules that are the weathering products of chemical weathering on the continents, end up in the ocean basins. The initial composition of ocean water in these primitive nascent oceans was not very salty, or not very saline, didn't have a lot of dissolved solids. Now, over time, as CO2 caused or controlled mechanical weathering increased or progressed, and this material was transported into the ocean basins, that is actually what made oceans saline or salty. So oceans, the salt water you see when you're swimming at the beach, or that you feel on your lips when you're swimming at the beach, is not really just salt water as in containing sodium chloride or table salt that lots of people use to season their food. It's actually dissolved rocks. It has lots of magnesium, lots of calcium, it has sodium, chlorine, aluminum. All the major elements that are represented in the Earth's crust are in the Earth's ocean, and that is in fact what makes ocean water saline. Oceans were also a sink for carbon dioxide. So as the carbon dioxide concentration in the atmosphere increased, ocean water has a tremendous ability, or water has a tremendous ability to dissolve gas phase carbon dioxide, remove it from the atmosphere, and become kind of balance out or equilibrate those levels. This became important for the formation of later biological organisms that use calcium carbonate to generate their cellular structure, or their shell structure, their skeletal structure. So how did those continents form? If you had a magma ocean at 4.7 billion years ago, how did anything change, and how did it get to the way it is essentially today? Well, as the planetary bombardment period ended, you had a lot less heat being generated on the outside surface of the Earth, and that liquid magma ocean started to cool and become more ductile, more fragmented. Plate tectonic motion initiated. You had mantle upwelling currents. You had gravity or density convection cells develop. And what you ended up with were lots of magma convection cells where you had divergence and subduction. So divergent cells, or divergent boundaries and convergent boundaries on a fairly liquid or malleable surface. We learned in chapter 7 that at subduction zones, oftentimes you get, or there's almost always volcanic island arc volcanism, which as plates are subducting, they're dragging down material down below. Water is incorporated into that, which reduces the melting temperature or reduces the temperature of magma formation, and magma eventually rises to the surface, erupting andesitic type flows, or andesitic type extrusions on the surface, and small little island arcs can form. So on an Earth surface devoid of any land area and devoid of any continental space, the simple act of subduction, or the simple process of plate subduction, could start to contribute, or could start to form small continental masses, small island arc masses on the surface. And as those subduction zones migrate and divergence changes and the plate tectonic system develops, you get accretion of island arcs on other island arcs. You start to have continental collisions. You start to have a continental to ocean subduction, which you get continental island arc volcanism, and intrusions, plutons, etc., start to form, and eventually you build up over enough time continental masses that are much more similar in size and scale and scope to what we see today. Some of the earliest rocks on the Earth are typically in continental interiors. The Precambrian, which is when all the continental formation took place, or most of continental formation took place, spans roughly 90% of Earth history, from 500 million to 4.5 billion years of time. Now, it's not well understood, because even though on this plot we see how the vast majority of rocks, these cratons, are from that period, they've been heavily metamorphosed, heavily altered, heavily deformed over time, and the story that's contained in those rock layers is modified incredibly, is modified extensively. It's like that chapter of the book, that the 90% of the book that you're reading, the story of the Earth, as a metaphor. It's as if 90% of that book, the words are rearranged, there's pages missing here and there, there's lots of chapters missing, words are scratched out, words are jumbled. It's basically a big mess. Most of the Earth's stable continental crust formed during the Precambrian due to tectonic partial melting of mantle forming volcanic island arcs and ocean plateaus. Accretion of those island arcs formed larger crustal provinces, and those crustal provinces were assembled with accretion into large blocks called cratons. And cratons formed the core of modern continents, and every continent there are large areas of Archean or Precambrian rocks, usually in the center. You can see Archean rocks form in the North American continent, the North American Shield or the Canadian Shield. There's outcrops of them on every continent. Now, supercontinents are an interesting concept that are useful for geologists. They are large land masses. They consist of nearly all, or all in some cases, continents. Supercontinents are fundamentally a product of tectonics or tectonism. They change over time. There's been several different supercontinents that have existed on the surface of the Earth. Rodinia is one. Pangaea is another. Gondwana land and Laurasia eventually joined to form Pangaea. Pangaea is the most recent one, but Rodinia was, true to its name, a supercontinent comprised of all of the continents that existed at that point in time. And splitting and reassembling of supercontinents have generated most of Earth's major mountain belts. So one could think of supercontinents as a cause, or supercontinents really as an effect of tectonics. And the collision of these or the tectonically generated collisions of these large plate masses are really what has given the Earth's major surface morphological features. What I mean by that is mountains, their character and location. Supercontinents are also very important over long periods of Earth science or Earth history, insofar as they can affect not just tectonic, or not just be affected by tectonics, and not just affect mountain ranges and surface morphology, but they can also affect climate. This is an example of a very, very important climate stage in the Earth's history. From 50 million years ago to present, we have the what's called the isolation, the strengthening of what's known as the Antarctic circumpolar current. A period in time, South America was actually connected to Antarctica, and this is when, as the breakup of Pangaea was occurring, Africa and India and Australia were moving away from Antarctica because they were all massed together. We can see that here in Gondwana. Australia, India, Africa, South America. As Pangaea broke apart, Australia's moved away, India moved away, Africa migrated, South America did too. However, it took some time for the South American continent to separate from Antarctica. And before that occurred, you had what are typically, and you'll learn about this in the next unit, what are called gyres. These are oceanographic currents that circle around ocean basins. You can see this general loop of ocean water moving in this large ocean. Over here we have similar gyre. It's a circular motion of ocean water on the surface in an ocean basin. Well, once this gap between South America and Antarctica was severed, the way atmospheric currents, or wind currents on the surface of the Earth go, the natural course of the natural current was actually what's called the Antarctic circumpolar current, or the west wind drift, which created a current that went or looped around Africa. If we could rotate this globe, we would see it. Instead of being isolated here and warm water coming down and cool water going back up into this basin, you had a strengthening of a current going around Antarctica, and it was very, very, very cold water. In fact, it was a positive feedback insofar it would get colder and colder and colder. And what that actually did was enable the generation of the Antarctic ice sheet, which is a massive ice sheet. It contains roughly 80 to 85 meters worth of sea level held on land. So the buildup of that ice sheet in Antarctica, which occurred over the last 50 million years, is entirely due, well, significantly due to the breakup of Pangaea, to actually supercontinent dynamics. Stepping quickly back to the Precambrian, a particular type of rock that's of great interest to geologists is what are called banded iron formations, and that's because geologists are particularly interested in the origin of life on Earth. Most people are, if you think about it. Life on Earth, or life as we know it, depends heavily on the fact that there's atmospheric oxygen. Well, scientists know that originally the atmosphere did not contain very much oxygen, if at all. It's only over long periods of time that oxygen built up to sufficient levels to support multicellular life. Banded iron formations are rocks that are Precambrian in age. They're 3.5 to 2 billion years old typically, and they're basically layers of alternating iron oxide and chert. Oh, they're beautiful. In fact, I have the banded iron formation picture right here. It forms the backdrop of the two lectures, two PowerPoint lectures of this unit. They actually illustrate the tentative beginnings of photosynthesis. And you say, well, how is that? Well, again, this is the story that's told in the rocks. Remember, rocks record the environmental conditions because they're a product of their depositional environment, the processes that cause them to be transported and deposited or formed in place, or altered and changed, this metamorphosis. Banded iron formations show red layers. You can see these red layers, and you can see the whitish layers. The white layers are chert, or a silica-rich silica dioxide. They're banded, which if you're paying attention over the last couple chapters, you know means they were deposited horizontally, oldest first, superposition, moving up to youngest, and what the red layers show are a presence of oxygen in the marine system. Now, why do the red layers show the presence of oxygen? Well, iron was ubiquitous and very, very abundant. We know that from initial atmosphere or planetary accretion processes, iron and nickel were abundant in the universe. We know most of that iron and nickel has migrated to the Earth's core. However, there's plenty of it left in the oceans and in the surface. In fact, it's so abundant in the marine system at this point in time that when oxygen would be added to the marine system, that oxygen, which joins readily with iron to form iron oxide or rust, would complex immediately and accumulate on the seafloor. So the red layers are layers of iron oxide. They represent a mineral that is the combination of iron and oxygen, and when they are present, they indicate that at that point in time there was plenty of oxygen with which to complex the iron. Now, the periods of chert or non-iron oxide imply periods of lacking oxygen. And so what this kind of alternating structure shows, no iron, iron, no iron, iron, or no oxygen, oxygen, no oxygen, oxygen, moving on up. Red means oxygen, white means little oxygen or less oxygen. What that basically implies is that at this point in Earth history, photosynthetic activity was just beginning, was kind of stopping and starting. It was a kind of a stop and go system where photosynthesizing organisms would theoretically bloom over long periods of time, and then things would happen that those would kind of not necessarily die out, but their impact or their location or their extent would decline a little bit to where chert deposition took over. When you find these beds, these banded formations, only in the period of time where oxygen was just starting to kind of accumulate in the atmosphere as it would equilibrate with the oceans. Once you got to the full oxygenated atmosphere, we don't find any banded formations at all. You find iron oxide for sure, but you don't find them in these well-defined banded environments. So the origin of life. A lot of people think a lot about it. A lot of people argue a lot about it. In this course, we use a science-based approach, and that is that the origin of life at this point in time is believed to have occurred due to something called organic synthesis. That is the natural combination, or the probabilistic combination of inorganic molecules into organic forms that eventually obtained or adapted and developed the ability to replicate, to trap and store energy, and to eventually to reproduce, and which is a form of replication, and metabolize. But Stanley Miller and Harold Urey, back in 40 something, graduate student and a professor at the University of Chicago, designed a simple experiment where they took a glass flask, a closed flask, filled it with gases that were thought to be some of the original primordial atmospheric gases: methane, ammonia, hydrogen sulfide, CO2. Put it in a flask with a boiling water underneath it in a closed loop system, and started to shock it with electrodes, simulating lightning. And what they found after several days of doing this loop experiment was that the inorganic compounds, the methane, the ammonia, the carbon dioxide, the hydrogen, the water vapor, those compounds were not the only compounds in their flask. In fact, they had developed, or they had synthesized, just due to these inorganic processes, amino acids. These are the basic building blocks of protein, basic building blocks of life. Now, whether the first life was formed in what are called the warm pond environment, which is volcanic areas with lots of warm water and lightning and on the surface of the earth, or in hydrothermal vents, which are deep in the ocean, where elemental or chemically rich fluids circulate through usually divergent boundaries, is still under great debate. But there is a it's not to the point of theory yet, but it's a very logical and a set of ideas in terms of the origin of life that most scientists work. It's at this point we'd be considered a solid framework for trying to figure out the details. So the general idea seems to make sense, and scientists are working vigorously to figure out the exact details of how you can go from inorganic synthesis, that is proven development, proven synthesis of organic molecules, to the point where these organic molecules can replicate and develop into evolved living forms. The first known organisms were single-celled bacteria, which are prokaryotes. They lacked a nucleus. Cyanobacteria were early photosynthesizers. They could synthesize organic compounds, produce their own food, and there's still fossil evidence remaining around the world, usually in formerly cratonic but coastal cratonic regions. Of these organisms, their layered mounds are called stromatolites. This is a cross-section or a slice of one looking down through, and you see these layers. They're basically layers of algae that accumulate over time. These are some real ones in Shark Bay, Australia. Layers of algae that precipitate a mineral skeleton or a mineral structure around them. They're thought to be the first, or at least they are the first fossilized life form that most earth scientists see. Now, the theory of evolution is not covered in this book very well, but it is part of the curriculum guidance for this course. So briefly, the theory of evolution is fundamental to biology and paleontology, and it explains the diversity and similarity amongst organisms that exist on the earth and have existed in the earth's past. It is a theory. It's accepted by the vast majority of Earth system scientists and biologists. It is not under debate that it is the dominant process by which speciation occurs, and how organisms adapt and diversify through geologic time. It's well supported by the fossil record. There are no quote-unquote missing links or gaps. There are details that all scientists love to fill in, because who cares about stuff we already know? Scientists go into science because they want to find out new things, and so the story is being filled in, the pages are being filled in, but generally the arc of the book is is well known. The theory of evolution is confirmed by empirical data, that it's not only just supported by the fossil record, it's not only a story that makes sense based on what geologists have found in the fossil record through Earth time, but modern experiments where actual observations are made of systems that evolve either very quickly or slowly. Empirical data has basically confirmed it. And the theory of evolution calls up the idea that random mutation and adaptation form the basis of what we refer to in the kind of common cultural vernacular as natural selection. That is, what most people think of survival of the fittest, which is not really a theory that is pertains to kind of human relations. I should caution you. A lot of people sometimes call up natural selection survival of the fittest when they're talking about cultural things. It's not really that. It's what it is it's a fairly agnostic view or a neutral view that organisms will naturally mutate over time, that successive generations will contain genetic mutations that may help them survive a little bit better than their ancestors, or it may make it worse. It may make it harder for them. Now, there's also another layer on evolution, and that is that the Earth system, as it impacts or as it relates to naturally occurring mutation and adaptation, that oftentimes an adaptation of an organism will be favorable under certain climatic or geologic conditions, but unfavorable for other geologic or ecologic or climatologic conditions. And so it's not only a kind of an organism-driven process, but the Earth itself, the framework on which evolution is built, and that organisms exist, or how the biosphere relates to the geosphere, can also be important. And the time scale of evolutionary change can range from billions of years to frankly minutes, with systems that are single-celled or microbiologic in nature. All right, so now we're going to go quickly through the modern. This is the post-Precambrian, or the period of Earth history that encompasses roughly the last 500 million years. The Phanerozoic is the age of life. It's dominated paleogeographically by continental collisions. Pangaea was assembled. Most of some significant mountain belts on the surface of the Earth, the Caledonian, the Appalachian, the Ural Mountains, were initiated in the Paleozoic, which is the first era of the Phanerozoic eon. It's often called the Age of Invertebrates because this is the dominant life forms that existed on the surface, and most of those were marine. In fact, they all were marine. Cephalopods, corals here, and sponges were dominant. Arose something called trilobites, which are the Earth's first recorded arthropods. Super cool fossils. Now we can see the evolution from the Cambrian to the Triassic, which the Triassic is the end of the or the beginning of the Mesozoic, the end of the Paleozoic. Gondwana is this continent down. It was a supercontinent down in the lower latitudes. Laurasia was this kind of quasi supercontinent that developed with Northern Europe and North America. And when Laurasia and Gondwana joined together, that actually formed Pangaea, which reached its peak at the Triassic, or the end of the Paleozoic, beginning of the Mesozoic. Paleozoic marks the first appearance of life forms with hard parts, or shells. And remember, in the fossilization part of the last chapter, hard parts are one of the most important criteria for fossilization. It's very, very difficult for fossils to be preserved if they don't have hard parts, especially fossils that are 500 million years old, 300 million years old. It's a lot of time for those fossils to be destroyed if they're not based on hard parts. The appearance of the first fossils with hard parts, so it resulted in abundant Paleozoic fossils. The life in the early Paleozoic was restricted to marine environments. Trilobites, cephalopods, sponges, corals, as we saw on the last slide. Diversification increased dramatically. In the late Paleozoic, insects and plants moved onto land. Lobe-finned fishes which arose in the early Paleozoic. This shows how a lobe-finned fish, which in the lobe of the fish, or the flipper, if you were, you see a lot of the same bones that you see reorganized into the foot structure, the ped structure of early amphibians. So lobe-finned fishes adapted to land and became first amphibians, and you had large, what are called coal swamps, tropical coal swamps in the Pennsylvanian period, which back a couple decades ago was known as the Carboniferous period in Earth history. But the Pennsylvanian Mississippian periods were characterized by hot, humid temperatures, hot, humid climates on the surface of the Earth, abundant plant matter growing in these environments, which eventually was deposited, lithified to form what we extract and use today as our coal resources. Now, the Paleozoic comes to an abrupt end after the Carboniferous, or after the Permian, or in the Permian, during the late Permian mass extinction. It's one of the greatest or largest extinctions that earth scientists have been able to discern from the fossil record, the rock record. It's where 70% of terrestrial organisms were wiped out and 90% of marine organisms wiped out. Now, there's a couple different hypotheses about how that could have happened. One is called a bolide impact, or a meteor impact. Bolide is another term for an object from outer space. Bolide impact, just like the one that we'll get to at the end of the Cretaceous. Bolide impact would cause dramatic effects on the surface of the Earth. Would impact photosynthesis. You have chemical changes in the atmosphere. It can be pretty much a nightmare for living organisms. Another hypothesis is that the large-scale fissure eruptions in the Asian and Eurasian plate, known as the Siberian Traps, where massive quantities of lava were extruded on the surface of the Earth, and the accompanying carbon dioxide that came with those eruptions would cause extreme greenhouse warming, which again can affect ecosystems dramatically. And another hypothesis, which is related to greenhouse warming, is the hydrogen sulfide poisoning due to rapid global warming caused by CO2 increase. Reduces the amount of oxygen in seawater. That is, as water temperature increases, the solubility of gases in water decreases. So warmer water means less oxygen dissolved. And where you have dissolved oxygen, you have lots of biology. Where oxygen is missing, anaerobic bacteria flourish, and anaerobic bacteria have a byproduct of their metabolism that is hydrogen sulfide, which is tremendously poisonous to animals and plants. And when hydrogen sulfide increases in concentration in the ocean, it equilibrates in the atmosphere, and you can get mass destruction or mass die-off in marine and terrestrial systems. Now, are extinction events like the one in the late Permian good or bad? Well, bad for the organisms that are becoming extinct, but from a long view process, or a long view of Earth history, extinction events actually open up new niches. They open up new space for organisms that survive those extinctions and can adapt and thrive in those newfound ecological space. So you'll see over the course of Earth history that in places where there's large extinction events, like at the end Permian, we had three major lines of organisms, of animals at this point. We had mammal-like reptiles, we had the beginnings of proto-reptiles here, and we had early amphibians. Now, at this end Permian, all of a sudden after that you see another more kind of diversification happen. You have early mammals arise, and after the end Permian extinction, dinosaurs expand, amphibians and fishes as well. And so extinctions are not necessarily bad as long as you're not the one going extinct. Now, the Mesozoic age, or the age of dinosaurs or reptiles, started roughly 250 million years ago at the beginning of the Triassic period and went to about 65 million years. It corresponds to the breakup of Pangaea. The North American plate moves away starts to override the Pacific plate, where you get causes crustal deformation and the orogenesis in the North American West. Sierra Nevada and the Rockies form at that point. And as we mentioned just a second ago, the late Permian extinction before the beginning of the Mesozoic made a lot of room for diversification of survivors of the Paleozoic. Notably, gymnosperms took hold. Now, gymnosperms are plants that have seeds that are not encased. So these are seeds that do not have an encasing shell. Things like conifers, pine cones, are basically seed-bearing structures. Conifers are important gymnosperms. Cycads are other important gymnosperms. And if you live in Florida, you'll oftentimes see cycads around. I love to call them dinosaur plants, because they're some of the earliest plants that really took hold on land. They're quite important organisms. The first reptiles were really small, but they did evolve rapidly, particularly the dinosaurs. And you saw that over here. We saw rapid diversification, rapid development of dinosaurs, which eventually moved, which a spur of that developmental or that evolutionary line was birds. Evolution occurred rapidly. Diversification was rapid with dinosaurs. Large carnivorous dinosaurs were present on the surface, and even larger herbivorous, that is, eating only plants, dinosaurs like Apatosaurus. And there were also pterosaurs, or flying reptiles. Archaeopteryx, which is the present or the predecessor of modern birds, arose at this time. And I like that notion of flying reptiles. It's not snakes on a plane, but there were flying reptiles, which is a interesting thought. At the close of the Mesozoic, at 65 million years ago, thereabouts, many reptile groups became extinct, but a few survived. Turtles, snakes, and lizards survived and were able to take advantage of new ecological space caused by that end Cretaceous extinction, which we'll get to right now. So along Barney, at 65 million years ago, a large bolide impact occurred. Most geologists agree now that it happened in the Chicxulub crater off the Yucatan Peninsula. This impact would have occurred right around here. Massive ejecta blanket. Ejecta is the dust that's blown up by an impact like that. Geologists find what are called ejecta minerals all around the Gulf Coast of the United States. You have to know what you're looking for, but it's basically little glass beads that are droplet or teardrop formed. You can find from the kind of the fiery explosion or fiery blast when that crater hit. Massive tsunamis are thought to have progressed around the Gulf of Mexico. You'll find massive overwash deposits in Texas especially. There is what's called an iridium anomaly, which is a layer of iridium blanketed around the Earth at 65 million years ago in stratigraphic section. And iridium is an element that doesn't really occur on the Earth's surface very commonly, but it is present in meteorites. So the explanation for that iridium anomaly, or the presence of iridium in a thin layer that's stratigraphically correlated around the globe, is that it was brought here from an extraterrestrial object that hit the surface. And 75% of all organisms were wiped out during the Cretaceous Paleogene extinction event, which used to be called, you'll find it in the literature, sometimes called the Cretaceous Tertiary extinction event. Cenozoic era, the era of modern life, starts at about 65 million years ago. Much of North America was above sea level throughout the Cenozoic. Eastern and western margins of the continent had dramatically different geology. The eastern margin on the Atlantic coast was very passive. They were far removed from the divergent tectonism that was occurring at the mid-Atlantic ridge after the breakup of Pangaea, whereas the western United States was undergoing active subduction, active mountain lifting or mountain building or orogenesis and deformation processes. The Cenozoic era is when the Antarctic circumpolar current developed, which I showed you a graphic of before, but this view is a slightly different one. This shows as the breakup of Pangaea occurs, as South America drifts away from Antarctica and Australia drifts away from Antarctica, this gap around Antarctica eventually widens enough where water can circulate in a loop type of current and maintain and cause a positive feedback, which encourages ice to form. Gets colder and colder, more ice forms, gets colder and colder, more ice forms, gets colder and colder. It's a positive loop that created has created the Antarctic ice sheet that we have today. The overall paleogeography of the Cenozoic world, going from older to younger. This actually starts at the youngest, going down, and oldest is down here. If we go from bottom up, we see the late Cretaceous breakup of Pangaea. By the middle Miocene, 10 million years ago, 15 million years ago, the continental arrangement is pretty much the way we have it today. And in the Cenozoic, mammals replaced reptiles as dominant vertebrate forms. Marsupials and placentals evolved. Mammals tend to get larger over generation and generation, so mammal groups tend to become larger. It's Cope's rule. It's actually Cope's Despartes rule. But late Pleistocene extinctions eliminated these large mammals, large animals. The larger animals need more energy, and oftentimes in periods of ecological stress, those animals or those organisms have a harder time surviving because the energy balance isn't there. Now, when food is plentiful, larger mammals, larger animals tend to do a little bit better because bigger can be better in many ways, which I think probably makes sense. The Cenozoic could also be referred to as the age of flowering plants versus the age of mammals. Angiosperms, these are flowering plants that had seeds contained in pods. Started to dominate relative to gymnosperms, but they didn't necessarily wipe out gymnosperms. They still exist today. And flowering plants strongly influenced the evolution of both birds and herbivorous mammals throughout the Cenozoic as food sources, and there's a synergistic evolution that take place there. So that's the end of chapter 12. I hope this was quicker. I'll see the time in a minute, and remember to take your chapter quiz. The next unit we're going to talk about is we're going on to the ocean system. We're going to depart from looking at strictly geological subject matter and moving into the other regions of Earth system science, that is oceanography, meteorology, and astronomy.